Good morning, everyone. Looks like we have 17 people here, so I guess that's good enough to get started. I hope you all had a good weekend. So we're a little behind on things right now. We are supposed to be starting today 7.3, right? That's what we're supposed to be starting, but we never finished 7.2. So we're going to spend the first part of class today finishing 7.2. I did extend the homework deadline for 7.2. It's due on, Tuesday night at right around midnight. And then the 7.3 homework, I went ahead and extended that until Sunday night. So you've got more time with that, because I don't know if we'll finish 7.3 today or not. I'm going to try to, but we'll see. All right. Are there any questions before I start? I have not put the homework solution videos for 7.2 yet because we didn't finish it, but I will do that hopefully today or tomorrow. Okay. All right, so let's get started. Let's continue with what we were doing last time. So the main idea from last time was that we were talking about if you have a right triangle that guarantees that the two other angles within the triangle will be acute angles. They'll be smaller than 90 degrees. And from that, we defined the 6 trig functions, sine, cosine, tangent. We define those to be a ratio of sides of the triangle. And then we use this SOHCAHTOA thing to help us. And then we need to remember that the cosecant, secant, and cotangent are just the reciprocals of the first 3. So the reciprocal of sine is cosecant, reciprocal of cosine is secant, reciprocal of tangent is cotangent. So all you're doing is flipping over whatever these values are, you're just flipping them. And we'll need that today, so I just want to make sure we're all clear on that. And then we did a couple of examples, and we got to this point here where I introduced the Pythagorean identities, and I showed you where the first one came from, and then we derived the other 2. All right, so just make sure that you're aware that those are there. And I did also post the formula sheet for the one that's used in calculus. I did post it in Canvas. So please get that, try and get it printed out as soon as you can. That way you can refer to it when necessary, and that way you know where all the different formulas are. You're not trying to scramble looking for those, first time you've ever used the formula sheet is on the test. I don't want that to happen, so make sure you get a copy of that printed out. Okay, so with everything we've done, let's go ahead and just take a look at these two examples, or this example that has 2 parts, and then we'll move on to the next one. So it says here, find the exact values of the following expressions, and it says no calculator. So the key here is that we are supposed to determine the value of what's presented here, this expression, but all we have to work with is what we know about the trig functions. So we have sine of 5 degrees divided by cosine of 5 degrees minus tangent of 5 degrees. Now, without a calculator, we don't know what sine of 5 degrees is. We don't know what cosine of 5 degrees is. So what I need you to understand here is we have, not good. We have a right triangle. That's terrible. Where, let me just start over. We have a right triangle where one of the smaller angles is 5 degrees. Let's say that one's 5 degrees. And what we're trying to figure out is what is sine of 5 degrees divided by cosine of 5 degrees minus this. Well, we don't know, right? We don't know because we don't know any of the sides. We don't know the lengths of the sides at all. So we can't set up ratios. So how are we supposed to do this? Well, we need to understand what sine of 5 degrees divided by cosine of 5 degrees is. And that we would go back and look at our information here and understand that, hold on, let me bring this up here, that tangent of any angle is sine of that angle divided by cosine of that angle. So we have to know that this is true in order for us to proceed with this. So we have to realize that this is really just tangent of 5 degrees. And then we're going to subtract tangent of 5 degrees. So anything minus itself is 0. So there's really no work to be done. The only thing we have to know here is that sine divided by cosine is tangent. All right, so most students know that, but that's a common thing that we're going to see a lot. So just make sure that you understand that. Any questions? Okay, what about the next one? Maybe somebody can help guide us on the next one. Let me first talk about it. It's cosine of pi over 12 squared plus 1 over cosecant of pi over 12 squared. Does anyone have any ideas of how we might be able to figure out what that is? Because we don't know pi over 12, we don't know any values. Again, we have a triangle that we don't know the sides for. So does anyone?
We can use one of the identities, correct?
Okay, so which identity would we use?
1 over cosecant squared is just secant squared, correct?
Okay, so we have to realize here now, I want everyone to understand this because again, this is one of those little subtle things that you need to be clear on. What we really mean when you see this notation is cosecant of pi over 12, all of that squared. That's what that little squared means. That little squared here really means you're taking the cosecant of pi over 12, not 2, and you're squaring cosecant of pi over 12. Okay? Now, the next thing I need you to understand is also very subtle, but this is the same as 1 over cosecant of pi over 12, that whole thing squared. Now, the only reason that that's true is because when you have a fraction and you square it, you square the top and bottom. So we have to realize that 1 up here is actually 1 squared. So that's why we're able to write it this way. Are there any questions on that? Does that make sense to everyone? Why this is this?
Yes, it
Now,
makes sense. But
say again?
it makes sense, but originally it's written cosecant squared, and then the rest. Why can't we just write it?
Hold on, I can barely hear you. Let me turn. Say it again. I had to turn my volume up.
Okay, so originally it was just written cosecant squared, and then like parentheses pi over 12 and all that. And then in the third and last one that you wrote, the whole thing is squared. Why can't we just write it like that originally?
You could have. You could have.
So that wouldn't be wrong?
It wouldn't be wrong if you just go from here to here. That's fine.
Okay.
I just want everyone to understand why it is that. Okay? Like, why is that become that? And as long as you're okay with that, we can proceed, right?
Yeah, I understand. I was just wondering why we couldn't write it like that originally, with where it looks like the whole thing is squared.
I understand. Okay, this little intermediate step was not necessarily something I had to do, but I was hoping it would make it clearer to everyone why it becomes this.
Yeah, I definitely did. So it's not wrong to write it like that in the first.
Yeah, don't worry about during, if you're doing work, you don't have to write all these little steps.
Okay.
In fact, you don't have to write any of this. What you really need to understand, let me just make a little more room here. What you really need to understand is that this is ultimately going to become, well, let's see, what is 1 divided by cosecant? So again, we go back to our relationships. If cosecant of cosecant of theta is 1 over sine, then that means that 1 over cosecant is sine. So they're reciprocals. So what we can do is we can rewrite this as sine squared of pi over 12. And that again is because that right there in blue is actually sine of pi over 12.
And then it's just equal to 1, correct?
Yeah, and then because we have cosine squared of pi over 12 here, then we can use our Pythagorean identity, right? Our Pythagorean identity says that if we ever have sine squared of anything plus cosine squared of the same thing, right? These angles have to match, then the answer is 1. So our answer here is 1, and there's no work. I mean, we're not doing any computations. We're just using identities to be able to turn it into something. Are we good? Anyone else have a question? These identities are going to be with us the rest of the class, and we're going to keep using them And we're going to get to a very, very difficult section in this class where we actually have to prove identities are true. And you'll see when we get there, students don't usually have a fun time with those. Okay, so let's look at the next problem. I'm going to start this on a new page. Okay, so this next problem is very different, all right? And this is definitely the type of problem that I like to put on tests, all right? It says if sine of theta is 1 divided by 5 and theta is an acute angle, find the other 5 trig function values of theta. So remember, there's 6 trig functions, right? I'm only giving you information about one of them. I'm telling you that sine of theta is 1/5. And then now you have to tell me the value of all the other 5 trig functions. So the way that we would do this is we would draw a right triangle. Now it doesn't have to be drawn like perfectly, just draw your triangle and then just pick theta. Theta can either be here or it could also be up here in this corner, but I'm always going to just stick it right here. Okay, and now sine, remember the SOHCAHTOA. Sine is opposite over hypotenuse, right? So that means that I could look at the 1 as being the opposite side, and I can look at the 5 as being the hypotenuse of the triangle, because it's a ratio, right? 1/5 is a ratio. So that means I can label the opposite side 1 and the hypotenuse 5. Any questions on that? Opposite over hypotenuse? The side opposite of the angle divided by the hypotenuse. Now, once we know 2 sides of a right triangle, we can always find the 3rd side. And we did this once last time. So I'm going to label this side, let's just call it A. And then real quick, I'm going to figure out what that is. So I know that A squared plus 1 squared must equal 5 squared. That's the Pythagorean identity. So that means A squared plus 1 equals 25. And I'll subtract 1 on both sides. So I get A squared is 24. And now at this point, I will take the square root on both sides. Please do not forget that when you take the square root on both sides of an equation, when you are the one who does that, okay? So if you're ever looking at an equation and you take the square root, then you must do plus or minus, right? Don't forget that. That's a college algebra thing. So what we're saying here is that A must be positive or negative square root of 24. However, A is the distance from here to here, right? It's got to be a positive number. So it can't be the negative root 24. So this has to be positive root 24. Questions? Okay, and then once we have that, we have all the sides. And once we have all the sides, we can figure out all the trig functions. So let's just run through this. We know that sine theta, we know that that was 1/5. Okay, cosine theta should be the adjacent over the hypotenuse. So is it Eza or Isa? Isa? Isa?
Isa, yeah.
Isa? How's it going?
Good.
Good. Okay. So what's cosine theta for us?
You said it's the opposite, like it's flipped?
Nope. Cosine, use the SOHCAHTOA. Cosine is going to be the A over H. So A stands for adjacent over the hypotenuse. So when you're looking at the angle theta here in green, the adjacent side is the side closest to it, which would be the A. So what's that for us?
24.
Square root of 24. Okay, square root of 24 over the hypotenuse, which is the longest side of the triangle, right?
Yeah, so
Which
5.
5. Okay, good. So there we go.
I had a quick
Right.
question.
Yes.
Can you reduce the square root of 24 more?
Yes, okay, so I think in our homework system, it wants us to do that, doesn't it? I don't care for that, but yes, you can. So what you would have to do is take square root 24
It'd be 2 and the square root of 6, right?
to, yeah, so you would look at 24 like, well, let me see, you go 4 times 6. That's square root 24, right? 4 times 6 is 24.
Mhm.
And then you can pull the 4 out as a 2, so that'd be 2 root 6. And you can't break the root 6 down anymore. So yeah, that's the way most likely the system is going to want to have you have the answer. On the test, remember you're handwriting your tests. If you leave it as root 24 over 5, I'm happy with that, okay?
Okay. Thank you.
Uh-huh. Okay, now the next thing is tangent. So we need to do tangent theta. And tangent theta is, using the SOHCAHTOA, is the opposite over the adjacent. So Leslie, what do we have for that?
I'm not sure, sorry.
I'm sorry?
I'm not sure.
Okay. So do you understand that tangent is opposite over adjacent?
Yes, I'm so sorry. My kids walked in and asking
Oh,
me
okay.
questions.
Okay, I'll come back to you. I'll come back to you. All right, how about Tyler?
Okay, so sorry, we're finding the tangent, right?
Yes, tangent. Uh-huh.
So that's opposite over adjacent. So then it's going to be 1 over the square root of 24.
Yes, good. Now I will accept that answer on a test, but we did talk about how they want you to rationalize, right? So this is again a college algebra thing where they don't like a square root in the bottom. So we would just multiply the top and bottom here by the square root of 24. And what that does is on top, you just get root 24. And on the bottom, when you multiply the root times the root goes away. So you just get 24 on the bottom. That's called rationalizing a denominator. So I'm guessing the system, the computer, when you type in your answers, I'm guessing it's going to want this, just like it wanted this. But again, on a test, I would take these answers. All right.
Yeah, that's what I had trouble on the homework was
Typing in the answer.
like I would get what you circled and
Uh-huh.
like I understand that, but then as soon as I would have to rationalize it, that's where like I was getting confused at first, but I finally understood like what it was asking.
Yeah. Yeah. So if you're having any trouble with this, like simplifying radicals or rationalizing denominators, that's a college algebra thing, and I'm happy to help you with that. Come into my office hours, or if you can't come to my office hours, go to the tutoring that's provided by the school and just say, hey, I need help with simplifying radicals or rationalizing denominators.
Okay, thank you.
Okay, so now the next step is for us to come up with the next 3, right? So we have the first 3. Now let's do the next 3. So the next 3 are just the reciprocals of these. So I'm going to start with the reciprocal of sine. The reciprocal of sine is cosecant. So all I'm going to do is take this fraction here in yellow and flip it over. And so I just get 5 over 1, which is 5. And then for cosine, the reciprocal of that is secant. So I'm going to take that answer and flip that answer over. So when I'm going to flip my answer over, I'm not going to do the one that they want. I'm going to flip mine over. So 5 over root 24. And then what you would have to do here is, again, rationalize the denominator. So you multiply by root 24, root 24. On the top, you get 5 root 24 over 24. And here's where things get real weird, because then you simplify this radical. So it becomes 5 times 2 root 6 over 24. So I already did that earlier. And then I can reduce, because 2 goes in 2 once and 2 goes in here 12 times. So you would get a final result of 5 root 6 over 12. We do not want decimals as answers, okay? We want the exact answer, so we want to leave the radical there just like that. And then the last thing is to get the reciprocal of tangent, which would be cotangent of theta. And that would be, I'm going to take, again, my answer and flip it over. So I'm going to do root 24 over 1, right? Which is just root 24. And you can leave that answer because that radical is not in the denominator. But that just becomes 2 root 6 again. So there you go. We have our 6, oops. I'll do the ones that the computer would want. These, oh, you know what? I never did that up here. Oops. This one right here, I never did 2 root 6 on top over 24, which would reduce to root 6 over 12. Sorry about that. So I'm highlighting in blue here the answers that the computer would want. All right. Any questions on this? You'll just do a few of these. You'll start getting comfortable with the whole, you know, rationalizing and simplifying roots. All right. That's that one. Okay. Yeah. So we can move on to the next one. Here's another one. Now, in the book, in the ebook, there is a set of steps to do that tells you like how to do this. You feel free to read through those on your own. I'm just going to go right to the problem again. So we have if tangent theta is 2 and theta is acute, then find the other 5 trig functions. So we have, again, a right triangle. I'm going to label theta. I'm going to write SOHCAHTOA up here. All right. So Angelique, are you there?
Hello.
Yes. How you doing?
I'm good. How are you?
Hanging in there. Okay. So what do you think? We're given tangent theta, right?
Mm-hmm.
And it's 2. So help me label the sides of this triangle. Tangent is opposite over adjacent, right?
Mm-hmm.
And here I have tangent is 2. So how could you look at 2 as a fraction?
You could look at 2 over 1.
2 over 1. Good. So we're going to write 2 over 1. And now, Angelique, what would my opposite side have to be then?
The opposite would be 2.
2. Everyone see that? This would be our opposite side. And then the adjacent side would be the 1. So I'm going to go 2 and 1. Everyone see that? Okay, so you have to realize that 2 is 2 over 1, or else you don't have a fraction, right? And then now it's just a matter of solving for the hypotenuse. So I'm just going to write down the Pythagorean identity, which is 1 squared. This time it's plus 2 squared must equal, let's label this side C, C squared. And so that means that we have 1 plus 4 is C squared. That means 5 is C squared. I take the square root on both sides, plus or minus root 5. And because, again, C has to be positive, that means C must be root 5. And then from there, you have all the sides. Once you have all the sides, you can get all the trig functions. We might have to simplify things, but we should be able to get them all. So I'm just going to write them all down here first. I like to write them like this, actually. This is the way I prefer to do it because I just put the reciprocals right next to them. So whatever I find out sine is, I'm just flip it over and that'll be cosecant, and just whatever cosine is, secant, and so on and so forth. So we know tangent was 2. So Allison,
Yes.
you there? Okay, Allison, you give me any 2 that you want. Okay, any 2 of these. I'll let you choose.
Like I just pick whichever.
Yep, whichever one you want.
Okay, we can do sine.
Okay, so what would sine be?
It would be. Would it be? It's part of the SOHCAHTOA, right? So it
Yeah.
would be the first one. So Opposite over hypotenuse.
Mm-hmm.
So 2 over 1. Oh no, 2 over the square root of 5.
2 over root 5. Okay, good. Now I'm going to keep going with you here. The computer's not going to want that answer. So what do I multiply the top and bottom by to get rid of the root?
Square root of 5.
Uh-huh. Okay. And so what do you get on top when you multiply across?
You would get 2 times the square root of 5.
And on the bottom?
Just 5.
Good. Perfect. Okay. Good job. Now, you want to give me another one?
Yeah, we can do. Is it the cosine?
You want to do cosine? Okay. What
Yeah.
would cosine be?
Adjacent over hypotenuse. So 1 over 2. Oh, 1 over square root of 5.
1 over root 5. And then you'd have to do the same thing we just did, right? With the root 5 on top and bottom.
Yeah.
Okay. So what would you get here?
So the bottom would be 5, and would it just be square root of 5?
Yep. That's it.
Okay.
Good.
Okay.
All right. Good, good. All right. So how about Lawrence? Lawrence, you there?
Yes, sir.
Are you following okay?
I'm a little bit lost.
Do you go by Quinn or Lawrence?
I go by Quinn.
Okay, I'm going to change it on my roster here. Okay, so you feel a little lost on this?
Mm-hmm.
Okay. So the first, are you okay, Quinn, with the idea that these 3 come from this SOHCAHTOA thing up here?
Yeah.
Okay. And then are you comfortable with the idea that these 3 are just those 3 flipped over?
Yeah.
Okay, so let's just go with that then. So let's go with this cosecant one. That should be the sine one flipped over.
So
Okay.
it'd be 5 over 2 pi 5.
Yeah, I would use the answer that we got in the very beginning. Okay, that one right there. Just flip that one over. Okay.
Okay.
So we just put square root of 5 over 2. And Quinn, we can leave that as our answer because the square root's in the numerator, not the denominator. So we can just leave it.
Okay.
Okay. So Quinn, what about this one? Secant theta. What would this one be?
Would it be square root of 5?
Yep, just square root of 5. And that's it, right? Because it's actually square root of 5 over 1 because we flip it, right? All right, you got this, Quinn. How about the last one?
Would it be 1 over 2?
1 over 2. Good. 1/2. So just everyone remember, this 2 is really 2 over 1, so we just flip it over. It's 1/2. There we go. Okay, so we have our 6 trig functions from that one angle.
I have a question.
Uh-huh.
Why for cosine is it just 5 and not 25?
Well, it is. It's actually this right here when you do it, root 5 times root 5. It actually becomes the square root of 25 because you
Okay.
multiply the 2, but then you take the square root of 25 and you get 5.
Got it.
Another way you can look at it is when you do these 2 multiplied together, you're actually doing the square root of 5 times itself. So you're squaring it. And when you square a square root, the square root goes away.
That's helpful. Okay, thank
Yeah,
you.
there's multiple ways of looking at it. So whichever way makes most sense to you.
Got it. Thank you.
Yep, no problem. Okay, so we're going to move on. The moral of the story here in the previous example is that if you're given the value of a trig function of an acute angle, right, just one value, you should be able to come up with all of them based on a triangle. All right. All right, so now we have a couple of theorems and properties that we need to kind of make sure we understand. The first one is called the complementary angle theorem. And it says 2 acute angles are called complementary if there's, well, this is just a definition first. 2 acute angles are called complementary if their sum is a right angle or 90 degrees. So when you think about a right triangle, right? When you think about a right triangle, if we call this angle theta, and let's call this angle beta, then since we know that this is 90 degrees already, right? That's 90 degrees. And I think Maddie said last class that they have to all add up to be 180, right? That means that whatever this is and this is also has to add up to be 90. So we know that theta plus beta must be 90 degrees, which means that theta and beta are complementary. They're complementary because their sum is 90. Okay, so anytime you have a right triangle, the two other smaller angles, the two acute angles are always complementary, always. Did you all see that? No matter what, it'll always be the case. So we get this very, very interesting result from this, all right? And this, I've always found this very difficult to read, all right? This table, I think it's easier if we just do a couple of examples, okay? So let me show you just an example. If I say sine of 10 degrees, okay? That will always be equal. So right now what I'm doing is I'm showing you what the theorem tells us, okay? The theorem tells us that if this right here is an acute angle, right? Then sine of that angle will always be equal to cosine of the other complementary angle. So that means all you have to do is think of what angle would you add to 10 to get 90, right? That would be 80, right? So sine of 10 degrees is equal to cosine of 80 degrees. That's what the theorem is telling us. This is a theorem. A theorem is a mathematical statement or that's been proven, all right? So we're not going to get into the proof of this. We're just going to take it and say, okay, we know this is true now. And this works for any acute angle. So if I go, what's sine of 3 degrees? Well, that's equal to cosine of what? Anybody?
87 degrees.
87 degrees. So as long as these two angles add up to be 90, this is true. And it works the same way with the other trig functions. We have it. It works with tangent and cotangent. Okay, so tangent of 40 degrees would be equal to cotangent of 50. See, 40 and 50 add up to be 90. And then it works with secant and cosecant. And you can, this is basically the theorem written right here. Okay. So think about it. If this right here said sine of 10 degrees, then what we would do is we take 90 and take away 10, that would be 80. And that's why this side would be cosine of 80. Now, this is a nice theorem, but quite frankly, it's not used a lot, but you should just know that it's here, okay? It will pop up every now and then, but it's not heavily used in the class, all right? Any questions on this theorem? Because I'd like to move on. We're gonna do a couple of examples right here, just to make sure we understand, because it gets a little harder once we have these in here, like radians. So I'll call on someone for the first one because it's the easier one. So how about James?
Yes.
James? Okay, so James, according to that theorem, I'm going to help you out here. This should be equal to cosine of what?
Of 28 degrees.
28 degrees. Everyone agree with that? Because 62 and 28 add up to be 90. Okay, so the next one, tangent, I'm going to give that one to So Young. Are you there?
Yes.
Okay, I'm going to help you out with this if you need it. First thing is that according to the theorem, cotangent, I'm going to highlight it here. Cotangent and tangent are the ones that are related. Okay, so we know that this will be cotangent. Now, So Young, how do you feel about the angle? Because it's not degrees, it's a little harder. If you're not sure, I'm going to help you. I kind of intended to anyway.
Do I need to convert to degrees, right?
You could, yes, you could convert to degrees, but let's try and do it in radians because we want to start getting comfortable with radians. I know that they're weird and they're a little intimidating in the beginning, but we do want to get comfortable with them. So what you need here is don't you need this, So Young? Don't you need whatever? Let's just call this thing in here. Let's just call this beta, okay? Do you agree, So Young, that whatever this angle is, plus this angle has to be equal to 90 degrees?
Yes.
Okay, but what's
Yeah,
90
90.
degrees? What's 90 degrees in radians? Do you remember? Go back to the circle
Pi
when we
over
drew the
2.
circle. Okay, pi over 2 is the correct answer. So here's 180 degrees, right? That's pi. And 90 degrees is pi over 2. So perfect. Everyone see that? Pi over 2 is 90 degrees. So would you agree, So Young, that the pi over 12 that we have here, plus whatever beta is, must be equal to pi over 2?
Yes.
Right? Okay, so let's solve for beta. So let's subtract pi over 12 from both sides. You with me, So Young?
Yes.
Okay, now here's the tricky part. I want to take pi over 2 and I'm going to subtract pi over 12. Right, that's really what we're trying to do on the right side.
Mhm.
When we've subtracted fractions in the past, So Young, what do we have to do in order to add or subtract fractions? What do we have to have here?
We suppose have same denominator or something?
Same
The
denominator.
same bar.
Yeah.
Yeah.
So can you think of a number that would be a common multiple of both of these or a common denominator?
6. I mean 12.
12, okay,
Yeah.
good. Everyone see that? 12, we could make both of these 12. So this one's already 12. So you'd have to multiply the top and bottom of this fraction by 6. Is that clear to everyone? Okay, so we get beta equals, let's see, we're gonna get 6 pi over 12 minus just pi over 12. And now that should be, let's see, here we just keep the denominator, right?
Mhm.
So Young, what do we get on top?
5 pi.
5 pi, right? So everyone, you have 6 pi and you take away 1 pi, you're gonna have 5 pi's. So beta should be 5 pi. Cotangent of, sorry, 5 pi over 12. So tangent of pi over 12 is equal to cotangent of 5 pi over 12. Good job. All right, how about the next one? Is it Michael? Michael Clark? Are you there? Michael? I don't see Michael. All right, how about Caroline?
Yes, sir.
Okay, same thing here. Cosine of pi over 4 will be equal to sine of, now same exact story. We want to call this, we'll call it beta again. And we want to make sure that when you add these two together, right, you get pi over 2. So I'll just write that down. We need pi over 4 is separate part. Pi over 4 plus beta to be equal to pi over 2. And so you're just going to subtract pi over 4 again, right, Caroline? On both sides? Wouldn't you do that every time, everyone? Do y'all agree as a class? Y'all agree? Every single time you do one of these, you're always just going to take pi over 2 and subtract whatever the other angle is. And that's why if you look back at the formula, do you see that that's what they're telling you here? They're saying, hey, if you want sine of theta, it's going to be equal to cosine of pi over 2 minus theta. This always has looked weird to me as a student. It looked weird, but I think once you kind of know what's happening, it's because that's what you're doing every single time, right? You're just taking pi over 2, subtracting.
I agree. Yeah, like now that we're like actually doing examples, that it makes more sense.
Yeah, and then here, these 6 is just the same as these, but in degrees, and that's easier because you're just doing 90 minus the angle, 90 minus the angle.
Just to be clear, in the bottom half of that table, theta is always in radians, correct? For that to work?
That's right. Yeah, this table, they should have it split like this, right? So it's,
It confused me at first because I
Yeah,
thought it was
yeah.
saying pi over 2 minus the degrees, and I was like, how does
Gotcha.
that
Yeah,
work?
everything here is in radians. And then everything above that is in degrees. They should have these as like little separate tables, I think. Or extend, they have a white line here, but it's hard to see it. They should extend that line all the way across, I think. Okay, so Caroline, did you get this?
Yes, it's beta equals pi over 4.
Pi over 4. So just 2 on top, 2 on the bottom here. You get 2 pi over 4 minus pi over 4, which is pi over 4. That's sloppy. So sine of pi over 4. Okay, let's move on. I think you could do the next one. All right, so now find the exact value of these without using a calculator. So when you look at this, secant of 28 degrees, cosecant of 62 degrees, again, we don't really know anything about 28 and 62 degrees. You know, we could draw triangles, but we should recognize that these are complementary angles, aren't they, right? They add up to be 90. So let's try and use one of our identities, or yeah, one of the identities that we just got. Let's leave the secant 28 degrees alone, and let's say minus. Now, we can rewrite this using the table from before. That should be equal to secant of 28 degrees, shouldn't it? Right? Cosecant of 62 is equal to secant of 28 because, oops, I went too far. Right? This right here. This relationship we have, or you could do it this way right here. Cosecant, I forgot what the problem is. Cosecant of 62 is secant of 28. So that's just going to cancel out and we just get 0 because they just kill each other.
Professor, how's that secant of 28 again?
Just looking at what cosecant of cosecant of 62 degrees. If we just started with this problem and I said use the table, you could come right here to this one and you could say cosecant of 62, replace that with 62, would be equal to secant of 90 minus 62. And 90 minus 62 would be 28. So it turns right into secant of 28. Yeah.
Yes, sir. Thank you.
Okay. Does anybody have a suggestion? How about Lauren? Lauren, do you have a suggestion on how we do part B? Is Lauren here? No, Lauren. Okay. Genesis?
I'm not sure.
No? Okay. Do you recognize that this 35 and 55 add up to be 90?
Mm-hmm.
Okay. So that means I can either convert the top one into cosine of something, or I could convert the bottom one into sine of something. So you pick, which one do you want to do? Do you want to convert the sine into cosine or the cosine into sine?
Cosine to sine.
Okay, so let's do that. So this would become sine of what angle?
Would it be 35?
35. Oops. Sine of 35, right? Degrees. So now this just becomes sine of 35 over sine of 35. And anything divided by itself is 1. So the answer would be 1. Does that make sense, Genesis?
Yes.
Okay. So this example right here was just illustrating how we can use the property. Now, please keep in mind, though, let's say that this problem right here that we just did, let's just say that that angle right there would have been 33 degrees and the bottom still would have been 55. We couldn't do this, right? Because then they don't add up to be 90 and we wouldn't have this nice thing happen. So they made the problem so it would work.
Sir, I have a question.
Uh-huh.
Isn't sine over theta, sine of theta divided by cosine of theta equal to tangent of theta? Couldn't you
It
do that?
is. It is. However, Cameron, please notice that we don't have the same thetas. So this is like sine of theta over cosine of beta. These two are not the same.
Oh, okay. Yeah, because I was a little confused. I was like, oh, okay.
Yeah. Okay, I'm glad you brought that up. We do have that sine of theta over cosine of theta is tangent theta. But it is very important to understand that that theta and that theta must be the same theta, must be the same angle. So since these two are not the same, 35 and 55, we can't just say it's tangent.
Okay, thank you.
Good, I'm glad you pointed that out. Well, we can't do that then. Okay, so let's see where we are here. I think we may be at the end. Yes, we are at the end. Just want to make sure. Okay, good. Okay, so that wraps up 7.2. And now I'd like to talk about the next section, 7.3. And I looked at the textbook and I was like, okay, you know, I could just follow the textbook, but I made a decision to kind of present this just the way that I want to present it. Is today the 8th? Is it the 8th?
Yes, sir.
It is the 8th? Okay, thank you. So I'm going to present this kind of the way I want to do it, okay? So, okay, so here's the main idea. Do you remember last class we were talking about those angles that everyone should get comfortable with, right? I'm going to go back to that. By the way, if this were a face-to-face class and you were sitting in my classroom right now, I would have started class by giving you a circle for you to fill out all the angles. It would have been a quiz. It's just we can't really do easy quizzes like that here. So the idea is that I would have expected that you would have that you could figure out what all these angles are. All right, so I'm just going to fill this out. I'm only going to fill out the first quadrant. That's it, just the first quadrant. The most important angles we had, this was 0 degrees. Then we had the one that was right here. This was 45 degrees and then 90 degrees here. Now, we also had this angle here, which was 30 degrees, and this angle here, which was 60 degrees, right? Now, all of those written in radians would be 0 radians, pi over 6, pi over 4, pi over 3, and pi over 2. All right, so we did that last class, but then I showed you how you can use these to count your way around, right? I just want us to focus our attention on the first quadrant right now, all right? So these are our common angles. And what you need to know are what the 6 trig function values are at all of those common angles. In other words, everyone here in this class needs to know what sine of 0 is, what cosine of 0 is, what tangent of 0 is, what cosecant of 0 is, what secant of 0 is. Oops, not theta, 0. What cotangent of 0 is. And so all 6 trig functions, okay, all 6, you need to know for each of these angles. All right. And so what the book does is they just give you a table. They give you a table to memorize. And that is not the way that we're going to do it. Okay. But does everyone understand? How many angles do we have here? Let's see. We have 1, 2, 3, 4, 5. So we have 5 angles, and we need to know all 6 trig function values at each of the 5 angles. So we need to know 30 different values, and we have to have them here. Okay, not on a calculator. We need to have them in here. So this is the way I'm going to present it to you, and it leads into something we're going to do in another section, what we're going to do is we are going to draw the unit circle. All right, we're going to start getting ourselves really acquainted with this, the unit circle. Now, the unit circle, we talked about circles at the beginning of class. The unit circle is a circle of radius 1. So I'm just going to go out here to 1, and I'm going to draw a circle. It's going to be not a very good circle, I'm sure. Whoa. Yeah, it's not good because it's white too, so I can't even see it. All right, so there's a circle. And the radius is 1. With me? So let's talk about, just in the first quadrant, the important points we know. We know that that point, as an ordered pair, as an x and y coordinate, is the point 1, 0, right? You go to the right one, you don't go up or down. And the point up here is the point 0, 1. Yes? Okay. Now, how about the point that is, if you were to go 45 degrees right here to that point, so let's say that's 45 degrees. I'm going to label it right here, 45 degrees. Then there is a point here, isn't there? It has an x and a y coordinate. Now, generally speaking, that would be something you don't know, right? Like, you wouldn't know what that point is. I'm going to tell you what it is, and you need to memorize it. The x and y coordinate of that point is square root of 2 divided by 2, square root of 2 divided by 2. You need to know that. Root 2 over 2, okay? Now, at 30 degrees, there's another point here on the unit circle, and that has an x and a y coordinate. So the x coordinate, again, you have to memorize this. The x coordinate is the square root of 3 over 2, and the y coordinate is 1/2. Now, we could get on our calculators to see what these numbers are, like as decimals, but we need to memorize them in their exact form, which is square root of 3 over 2 and 1/2. Does everyone understand that I am telling you this and you were taking it on faith and you're just like, okay, I just need to know that now, all right? This is not like me trying to explain to you why it is this way. Just here it is, all right? Now, the other angle here that's important to us is 60 degrees. And that point is 1/2 root 3 over 2, which conveniently is just this one flipped over, isn't it? They just, x and y coordinates change. So there aren't really a lot of things for us to remember. I think the 1, 0 and the 0, 1 are easy. Would you all agree with that? These two should be easy to remember. The one in the middle, right, is just root 2 over 2. You just got to remember that's the x and y coordinate, right? So it matches. Then the other one, well, these two you have to remember, and you just need to remember the order of those. So here, I'll tell you how I remember the order, okay? The way that I remember the order is this. When you're at this point right here, I'm going to highlight it in red here. That means you have to go out to the right and then up, right? Like this. To get to that point. What is bigger? The movement, the rise or the run? Let me put it that way. To get to this point, what's bigger? The rise or the run here?
The run.
The run. And the run is the x coordinate, isn't it? And so do you all agree that square root of 3 over 2 is bigger than 1/2? Why is root 3 over 2 bigger than 1 over 2? They have the same denominators, don't they?
Root 3 is bigger than 1.
Root 3 is bigger than 1, right? The square root of 3 is a number that is bigger than 1. And so the way I look at it is when I am trying to remember which goes first, is when you're at 30 degrees, you have the X is bigger than the Y. So that means that this number has to be the bigger one. But when you go to the other point at 60 degrees, look at your run is only this much and your rise is bigger, right? And so the √3/2 goes on the Y coordinate. Hopefully that helps for you to remember the order. You still have to remember √3/2 and 1/2 go together, but you just have to remember which order, okay? That makes sense? Okay, so why am I showing you all this? Well, I'm showing you this because we have a very, very nice relationship between the unit circle and our trig functions. And this is actually coming in a later section, but I'm giving this to you early because I just don't like the way this section presents it, because it seems like you have to memorize a table when later on you don't. So here's what we are going to get now. If you have the unit circle, okay? So unit circle, we have to be on a unit circle. And you take this circle and you look just in the first quadrant here, okay? If I give you any angle, doesn't matter what it is, okay? Let's call that theta. Then this point right here, X, Y, right? This right here, this point has an X coordinate and a Y coordinate, right? Yes? Now, if it's 30, 45, 60, then we know the X and Y, don't we? But generally speaking, this is any point on this unit circle. Here's the big deal, all right? How we connect this to the trig functions. Well, we know, what I'm telling you is true, is that the X coordinate will always be cosine of the angle, and the Y coordinate will always be sine of the angle. Always. That's a big deal right here. Okay, this is a big deal. Okay, the X coordinate is always cosine. So sometimes the way we write this is not like this. What we do is we write it like this. Cosine of theta, sine theta, like that. So why is this important? Well, now I can ask you for the trig functions at any of the common angles. All you have to do is determine whether or not I'm talking about the X or Y coordinate. Let's do some examples to see if you understand this. So if I ask now, I'll just do this over here. So examples here. If I ask you, what is sine of 0 degrees, then Yamna, are you there?
Yes.
What is sine of 0 degrees?
Is it 0?
It is 0. So can you tell me what you're thinking when you're doing that? Like, did you already know sine of 0 was 0, or are you using what I just gave you here?
I looked at the unit circle.
Okay, so you're looking at the unit circle. You're looking at 0 degrees, which is here, right?
Mm-hmm.
And you're giving me which coordinate, the X or the Y?
I guess Y.
You're doing the Y. And why are we doing Y, everyone? Because Y is sine of the angle, okay? So let me just recap. That's correct, Yamna, thank you. So the way you should be thinking about this is when you see sine of 0 degrees, you should be thinking, okay, I'm on the unit circle, I'm at 0 degrees, I'm thinking about what the ordered pair is there, right? The ordered pair is 1, 0. And because it's sine, I'm thinking about the Y coordinate, and the Y coordinate is 0. So my answer here is 0. Look at that as opposed to this one, cosine of 0 degrees. It's the same question, same angle, same point, but now which coordinate are you looking at?
The X
coordinate.
The X. And what's the X coordinate there?
1.
1, okay? So cosine of 0 is 1. Does this make sense? We're going to keep going. We're going to go around and do some more. How about this one? What is sine of 60 degrees, and I'm asking Jackson.
Yes.
Okay, what's sine of 60 degrees?
So the y would equal 60. I'm kind of still confused on this.
Okay, so Jackson, if we're looking for sine of 60 degrees, the way I want you to think about this is because we're talking about sine, I want you to be thinking y coordinate, okay? So go to your unit circle, go to 60 degrees, and give me the y coordinate of that point.
It's square root 3 over 2.
Square root 3 over 2. Okay, you're not off the hook, Jackson, because I gave you that one. So Jackson, what's cosine of 30 degrees? So it's cosine this time.
Yeah.
So I'm talking about, go ahead.
Square root 3 over 2.
Square root 3 over 2. Because now we're talking about cosine, we're talking about the x coordinate, but we're talking about 30 degrees. So Jackson's going to the x, here's 30 degrees going to root 3 over 2 here, right? The x coordinate. Good. Moving on here. Jordan? You there?
I'm here.
Okay, Jordan, is it making sense?
Yeah, it's making sense.
Okay, because I'm going to give you a harder one. You ready?
Yeah.
Okay, so I'd like to know what tangent of 0 degrees is. Now, this is intentionally tricky and I haven't done this yet. So what do you think, Jordan?
I'm not sure.
Okay, do you know anything about tangent and what tangent is in relation to sine and cosine? I'm going to go back this right here. So remember that tangent theta is sine theta over cosine theta? Yes?
Yes.
Yes? Okay, so if you don't have that memorized, everybody, you'll need to try and get that one memorized for sure, okay? Tangent theta is sine theta over cosine theta. So if that's true, then Jordan, couldn't we rewrite this as sine of 0 degrees over cosine of 0 degrees?
Yes.
Okay, so now what is sine of 0 degrees?
0.
0, okay. And what is cosine of 0 degrees?
1.
1, and 0 divided by 1 is 0, right? So tangent of 0 degrees is 0. Jordan, does that make sense?
Yes.
Okay, good. Okay, Michael, you here?
Yes.
Okay, you get another harder one, I think.
Okay.
So here we go. I would like to know what cosine of pi over 4 is. So I've switched it up to radians now. So Michael, are we looking for the x or the y coordinate?
We're looking for the x.
X, because it's cosine, right? Okay.
Yes.
And you just need to know where pi over 4 is.
Yeah.
Do you know where it is?
It's isn't it 45 degrees?
45 degrees. Okay, good. So
So
what
it'd be
is
square root of 2 over 2.
root 2 over 2? Okay. So look, here's what I'm trying to get across to everyone. One way we could do this is the way the book does it. Let me see if I can show you the way the book does it real quick. Bring this up. Do I still have it up? Oh, yeah. I'll show this to you. Hold on, let me just bring up the page first. Where is it? Oh, here we go. So the way the book does it is they give you a table and they say, okay, here are the common angles, 30 degrees, 45, 60. Here are those in radians. And then here's a table, just memorize the table, right? That's one way to do it. I personally don't like that. If you like that, then go ahead and go memorize that table. I like something visual to connect it to. So that's why I'm giving you this, all right? So let's do some more, okay? Let's do some more because these do get a little bit challenging when we start doing things other than sine and cosine. Let me copy this and take it with me to the next page. Okay, so let's try this. How about what is secant of 60 degrees? All right, and we are at, let me see, I've lost my spot here. There we are. Samuel?
Yes.
How's it going, Samuel?
Good.
Okay, secant. This circle only tells us about sine and cosine, right? That's it. So in order for you to do this, Samuel, you're going to have to tell me how secant is related to sine and cosine. Sine or cosine. Any ideas? Do you know what secant is the reciprocal of? It's either the reciprocal of sine or cosine.
Cosine.
Cosine. So that means, Samuel, you can write this as 1 over cosine of 60 degrees. All right, Samuel, what is cosine of 60 degrees?
Are we gonna do the 90 minus thing?
No, off of this right here. If I'm asking for cosine of 60 degrees, you're going to go to 60 degrees on the unit circle and you're going to give me which coordinate, the x or the y?
Oh, the x.
The x, which is?
1/2.
1/2. So this is 1 over 1/2. And 1 divided by 1/2, you flip the 1/2 up like the reciprocal, and this just becomes 2. Secant of 60 degrees is 2. All right. And again, we could just memorize that right here. Secant of 60 degrees is 2, right? We could just memorize the table. Some people like to memorize. Okay, how about this? Cotangent of 45 degrees. And let's go with Cameron.
Yes, sir.
What do you got?
Well, since cotangent's inverse is tangent and tangent is sine over cosine, wouldn't you just take sine of 45 divided by the cosine of 45?
Other way, you could do it the other way around. So here's what I heard you say. You said cotangent is the reciprocal of tangent, right? And then, yes, I agree we can write that as 1 over sine of 45 over cosine of 45. Yes. If that's what you meant, then yes, you can do that. Yes? But do you also agree, before we do anything else, do you agree that we could also just flip that right now and make it cosine 45 over sine 45?
Yes, because you take the reciprocal.
Yeah. So think of it this way. If tangent is sine over cosine, and cotangent is cosine over sine, right? Okay, so that's where we are. So do you want to go ahead and tell me what this would be then?
So you would just divide the square root of 2 over 2 divided by the square root of 2 over 2. So wouldn't that just, oh, go ahead.
Yeah, which is what?
Wouldn't that just cancel out?
It would become a 1. Yep. So cosine of 45 degrees is the x coordinate at 45 degrees, which is root 2 over 2. Sine of 45 degrees is the y coordinate at at 45 degrees, which again is root 2 over 2. So this is root 2 over 2 over root 2 over 2, which is 1.
And then Professor, we flipped it, we flipped the cosine and sine over because it was the 1 like we're dividing by 1, correct?
Well, because it's 1 over that fraction.
Okay. And then
Same
that,
thing we did here. Anytime you have 1 over a fraction, you just flip the bottom fraction over.
okay, thank you.
Okay, next one is going to be, let's see. Maddie, you get, oh, I need to give you one. How about this one? How about cotangent of 0? So things can get weird here.
So that would be 1 over tangent of 0 degrees.
Okay, so you want me to write that as 1 over tangent of 0. Okay.
And then that would convert to 1 over sine of 0 over cosine of 0.
Okay.
And sine of 0 is, that was the, sine is the y coordinate, correct?
Sine is the y coordinate.
So that would be 0 over 1.
0 over cosine of 0 is 1. Does everyone follow that? Look, and let me just say, there's multiple ways that you can look at this. We should all get the same answer. So if you're looking at this slightly different, like if some of you may say, oh, okay, cotangent of 0 is just cosine of 0 over sine of 0, just like we did in the previous problem, right? Cotangent of 45 turned out to be cosine 45 over sine 45. If you do that here, that's fine. This is the way that Maddie is going, so we're going to go this way. It's not wrong. So, but something weird is about to happen. We have 1 on top. Maddie, what's 0 divided by 1?
0.
0. Uh-oh. 1 divided by 0.
It's an imaginary number.
It's, yeah, it's not a real number. It's undefined, right? We cannot divide by 0. So this is the first time this has happened. We are going to say that this is undefined. Undefined is our answer. And the reason it's undefined is because we have division by 0. And again, if you're one of those people who want to memorize this, oh, do they not even do that to you? Oh yeah, they stayed away from certain places. Okay, I see. Yeah, that's boring. Okay, undefined. So we can get undefined as an answer if we get division by 0, right? It's possible. All right, let's do one more. We haven't done cosecant. Let's do cosecant. What is cosecant of pi over 6? And this will be Joshua.
Yes, sir.
Okay, cosecant. So cosecant is the reciprocal of what trig function? One of basic trig function. Sine or cosine?
It is sine.
Sine. So we go 1 over sine of pi over 6. Okay, so Joshua, what are you going to do for the sine of pi over 6? Tell me what you're going to look at on this circle.
So I would look, so I know that's 30 degrees. So I already know that cosine is √3 over 2 and sine is 1 over 2.
1 over 2, okay. So this is going to become 1 over 2, right?
Correct. Just going to become the same thing.
Just flip it and it just becomes 2, right? That's it. Does anyone have any questions over this? Does everyone understand the importance and the value of understanding what's happening in this first quadrant?
I have a question.
Yes.
So cosecant is or hold on. So it is sine, right?
It is sine.
And sine is the y, so wouldn't it be √3 over 2?
But we're at pi over 6 is 30 degrees.
That's what it was.
Yeah, so
I
be
put it
careful.
with the
Were you at
60.
60 degrees? Yeah. So just
Yeah.
be careful. that's where knowing these in radians, the sooner you kind of memorize these, the better. But you'll make little mistakes. It's okay.
Okay.
You don't want to make them on the test. That's all. So yeah, so we're at pi over 6, y coordinate 1/2. I was going to say something else about this. Yeah, understanding what's happening in the first quadrant, the value of that. Oh, I was going to tell you, like even in my calculus classes, like I'll get to my Cal 1 class and I'll be going over something and we'll have to figure out, like usually very early on in the class, I'll be like, okay, all right. And then we get this and it's like cosine of 0. And I'll be like asking the class, okay, what's cosine of 0? And they're like, just silence, like crickets, you know? And that's always so very, very disappointing to me. Not because I expect everyone to know what cosine of 0 is, but once you understand the unit circle, right? Do y'all see how that's a very simple question? Like cosine of 0 is the x coordinate when you're at 0 degrees. So if you have just a basic visual like image in your mind of what the circle looks like at 0 degrees, you know, you're here, right? As long as you know that cosine is the x coordinate, then it's just 1, right? Cosine 0 is 1, sine 0 is 0. That should be a very simple question to answer in a Cal 1 class. That shouldn't be something that stumps everyone. And what's even, and it's not my students' fault. It's the way it's taught to them in pre-cal. And what gets to me even more is when I do what's cosine of 0 and then I see this. That is really, I mean, that's almost like, I'm sure you have friends that are not real mathy people and you ask them, you know, what's 12 plus 7? And they're like, let me get my calculator out. You know people like that, right? It's okay, it's not bad. It's just people become dependent without actually thinking. They become dependent on this for the answer. When if they just understand it a little bit, it's not a hard question. So you definitely want to get to a point where you're in this class and you carry it on into calculus, where if somebody asks you what one of the basic trig functions is, like sine or cosine, at one of the common angles, it should be something that just kind of flows from your mind. So take time to invest time into this quadrant. The more time you invest in that, the better off you're going to be as we proceed. And then later, very soon actually, we're going to throw in the other 2 quadrants. So very soon I'll be asking not what is sine of pi over 6, but I might be asking you what sine of -7 pi over 6 is. So then you've got to go like count like clockwise to 7 pi over 6. You got to know where that is and then grab me the y coordinate. So the rest will come later, but we can't do the rest if you don't know the first quadrant. You've got to have the first quadrant down. All right. Okay.
Will we ever need to apply these theorems to a circle other than the unit circle? Like
it will extend out
combine
to, yes, it will extend out to circles that don't have a radius of 1. And then that's when we'll get our final definition of what the trig functions are. Yeah, but it'll still come from a circle. Everything will, and you'll still have the common angles. So it'll all flow very nicely. All right, we good? All right, now the last thing, not the last, second to last thing, is that, well, sometimes we need to know the value of trig functions at angles that are not common. So we do need a calculator. All right, so it's calculator time. Okay, so calculator. So I'm just going to put a couple of problems up here and you just make sure you have a calculator that can do these. I want to know what sine of 12 degrees is. I want to know what cosine of 48 degrees is. I want to know what tangent of, let's go with 18 degrees is. And then after that, I want to know what sine of 1.7 is, what cosine of 0.98 is, and then how about tangent of 1.2. All right. So what you're going to do is get your calculator out. And everybody's going to have a different calculator, right? And just remember that on your exams, right, that you take, the exams that you're going to take here in the Zoom session, you may not use your phone as a calculator, which means you have to be using something else, right? So you want to make sure that when you're doing these, you're getting yourself acquainted with your own calculator. So the first three that I'm asking you to do, I'm giving you the degrees, right? The angles in degrees. So you want to make sure that your calculator is in degree mode. And every calculator is a little different. So you're going to have to figure out on yours how to switch from radian to degree. So I just switched my calculator to degree. I'm just going to give you the answers, and then it's going to be your job to make sure you can get the same answer on your calculator. So for the first one, you get approximately, I'm going to round, 0.2079. I'm going to go 4 decimal places. Approximately 0.6691. Approximately 18 degrees. So 0.3249, something like that. So I want to kind of illustrate to you what we just did, all right? And then we'll get to the other answers. Let's just look at this first one. What is that number, 0.2079? What is it, right? So here's what it is. If you take the unit circle, right, where this is the 0.10, if you were to go to 12 degrees, sine of 12 degrees, remember sine is the y-coordinate, right? Sine is the y-coordinate. That means that here's what I can tell you. The y-coordinate of that point is 0.2079. That's how far up you are, 0.2079. That makes sense? Now on the next one, this one, cosine of 48 degrees, what that means is if you go to 48 degrees and you look at which coordinate this time?
The x coordinate.
The x coordinate, it would be 0.6691. And then tangent of 18 degrees would mean if you go to 18 degrees, well, tangent gives you the sine over cosine, doesn't it? So this is a weird answer because what this answer is sine of 18 degrees over cosine of 18 degrees. That's what 0.32 is, 3249 is. So I want you to look at this way. This is your y coordinate, and this is your x. So all this is saying is for this point right here, if you take this y coordinate and x coordinate, if you take the y and divide the x, take that number and divide it by that number, you get this number. So we still don't know what these two numbers are, right? We just know that their ratio is this. Okay, let's do this. So you switch to radian mode on your calculator. Anybody have a question? No? Okay, sine of 1.7. Uh-oh. I get approximately 0.9917. I rounded. Cosine of 0.98. I get approximately 0.5570. And then tangent of 1.2. You get about 2.5722, something like that. All right, you all good? This is just a calculator exercise, that's it. Now we're actually ready to do something useful with this, okay? We're gonna do something useful. Applications. So let's say that you're standing next to a very large tree. All right. Here's you. You're standing next to this very, very large tree. It's impressive, I know. So there's this tree. And what you have, okay, what you have with you is a calculator. Okay, so you have a calculator. You have measuring tape. Okay, so you have a way of measuring. And you have a way of measuring angles, so like a protractor. Does that make sense? So you have with you, you have a calculator. You have measuring tape. Like a tape measure, right? And you have a protractor. And a protractor is what you do to measure angles. Y'all know what I'm talking about? Protractor? Y'all seen these?
Mm-hmm.
Okay, so, and let's say that this tree is very tall. There's no way you're going to climb this tree, okay? How could you estimate the height of the tree?
Wouldn't you get the angle of elevation?
Okay, so you could measure an angle, right? So you called it the angle of elevation, and that would be, let's say, from where you're standing to roughly the top of the tree. So that angle, maybe you could measure that angle. I don't need 2 lines. So maybe you can measure that angle. We'll call that theta. Does everyone agree that you could approximate that maybe with your protractor? Yes? Okay, yeah, I agree. We could measure that and we would know it, right? So theta, we would have a check mark. We would know what that is from the protractor. Okay, what next?
The distance from the tree.
To what?
To the person viewing the tree.
Okay, so you could get your tape measure out and you can measure from here to you, right? Let's call that, I don't know, A. And we could figure out what A is using the measuring tape, right? We could do that. Now, does everyone see that this forms kind of a right triangle? Yes? Now, let's say we did this, okay? I need to show you, like, let's act like we actually did this. Let's say that we did this measurement, and let's say that we found that this angle was 67 degrees, okay? And let's say that when we measured the distance from us to the tree, let's say that that was 32 feet. What we're interested in knowing is how tall this tree was, which is this side over here, which I'm going to call this, I could call it anything I want. I'm going to call it H for height. Y'all okay with this? Now, Sierra, are you there?
Yes, I'm here.
Okay, Sierra, so important question for you. We know this side, well, sorry, we want that side and we know this side, right? So that's the what side and what side? SOHCAHTOA, that's the what side and what side?
Adjacent
Mm-hmm.
and opposite.
Opposite. So Sierra, we want to know what the opposite side is, right?
Mm-hmm.
We know the adjacent side, right?
Yeah.
What trig function connects opposite and adjacent together? Is it sine, cosine, or tangent? So think SOHCAHTOA.
Tangent.
Tangent, right? Everyone SOHCAHTOA? SOHCAHTOA. So we have our hypotenuse and our adjacent and our opposite are these two sides, and tangent is the one that connects those. So Sierra, last thing I'm going to ask you, how could I write this down? If I know that this angle is 67, how could I write this TOA down using all this information? So tangent of what? What's the angle?
67.
Okay, tangent of 67 degrees must be equal to what? Tangent is opposite divided by adjacent. So what do I write here?
Would it be h divided by 32 feet?
Yep. Okay, good. I'm going to leave the feet off. Good,
Okay.
Sierra. That's all for now. Does everyone understand what we just did? We used the tangent function and the fact that tangent is opposite over adjacent to create an equation, right? And the thing that we want to know is right here, h. Everything else we know, or we could use our calculator to get. So right now I'm going to isolate h by multiplying both sides of this equation by 32.
You can just cross multiply too, right?
You could say cross multiply, that's fine.
Okay.
All right, so multiply this side by 32 and this side by 32. We cleared the fraction over here so we can get h by itself. And now everything here is just your calculator. Make sure you're in degree mode. I was in radian, and you should have been in radian also if you did those problems from before. 32 times tangent. Someone want to tell me what they got?
75.3873 feet.
Yeah, 387. Yeah, this is close enough. We were approximating it. I mean, we're using a protractor, you know, so it wasn't probably not that accurate, but this is how many feet tall. That's a pretty tall tree. Yes, that's a pretty tall tree.
So I have a question.
Mm-hmm.
Did you just did you just calculate tangent 67 on the calculator and then multiply it by 32?
Yes.
Okay.
The tangent of 67, make sure you're in degree mode, and then multiply that times 32.
Okay.
Or on some calculators, you can just type it all in at one time.
Okay, thank you.
Okay. So this is actually very, very powerful because we measured the height of the tree without actually ever having to get up there and measure the height of a tree, right? Now, let me show you a different application of this. What if we're looking from the top down on this scenario? We have a river. So we're standing here on this side of the river. This is all water in here, okay? And we want to know the distance across this river. Okay, so we would like to know this distance. Now, don't think of this as like a little stream. Think of this, if you've ever been to like Louisiana and have seen the Mississippi River, like that's a real river. Like that's, you know, you can't say, oh, that's about 20 feet. Like there's no way of measuring that easily. And you're not just gonna go across real fast, right? So if we wanted to approximate the distance across some significant river, or even think of this as like a cliff, or not a cliff, but think of it like what do you call it, the Grand Canyon or something, where you can't get to the other side easily, right? And you want to estimate that distance. Then what you could do, let's say we're standing on this side. So say that's me. Okay, that's me. Looking from the top, I'm wearing a black hat. Okay. And now what I'm going to do is, again, I have a protractor, I have a calculator, I have a tape measure. So what I can do is just pick any other point on the river, down the river here. I can measure this distance. Let's say I get that that's, I don't know, let's say that I measure 100 feet over. I just decide I'm going to go 100 feet that way. And then I can measure the angle from here to here. And let's say I measure that to be, I don't know, 13 degrees. And do y'all see how you could again find that distance across the river? Now, have you ever seen, like on the side of the highway when they're building buildings or, you know, building roads, have you ever seen those people sitting there with the tripods and they're looking through those things? That's basically what they're doing here. Now, technology has come a long way now, so they can use other things like GPS and lasers. But like before all that, it was very much just angles and saying, okay, if I want to measure distance from there to there, then I can just create this triangle and use the trig functions. All right, so let's do this one. Why don't you do it on your own? We only have 5 minutes left. See, I'll call on somebody here. I still have Brianna, Karen, and Anna Marie. So I'm going to call on one of you. Everybody find that. See if you can find that distance. I'll give you like 1 minute, 2 minutes. Set up the equation. Be right back. Okay. Brianna, Karen, or Anna Marie? I'll take a volunteer.
I can go.
Who's that? Brianna?
Anna.
Oh, wait, Anna Marie. Okay,
Yes.
yes. Go ahead. Did you get an answer?
Yes, I got 23.09 feet.
23.09 feet. Anyone concur with that? Agree?
I agree.
Agree. Okay, so this river's not very wide. That's the way it is. Okay. If this would have been a bigger angle, then it would have been a much wider river. So what'd you get? What'd you get again? I'll write it down just so we have an answer.
23.09 feet.
Okay, so make sure you can get that. We're setting up this equation. We have 13 degrees here. We have, we'll call this, I don't know. Did you call it H? You call it whatever you want. 100, let's call it H. So we have tangent of 13 degrees equals H over 100. And then you do the same thing. Now, believe it or not, this is a way that people back in a long time ago estimated the distance from like us to the moon, like how far away the moon was from us. Same thing. You could do something like, you know, you're sitting there, you're looking at the moon, right? And you're sitting here looking. Here's your eyeball. Okay. Here's my hat. Okay. So there's my eye. So you could look at something like that. It would be an estimate, but you could try and measure this angle. Well, this is a little more complicated than this. You try and measure this angle, and then you do another triangle right here, and you do similar triangles. I'll get to an example like that. We're out of time. So, but I'll tell you that all of this is pretty much what we have used for a long time to try and estimate astronomical distances. Okay, that should be enough to do everything through 7.3. I'll have to go through the homework myself to see.
Can I ask you a quick question about
Yeah, go ahead.
On problem 15, I was wondering if there's an easier way to reduce the square root.
Problem 15 from where? Which section?
7.2.
7.2. Okay, I'll go into that and take a look at it here in a second. Anyone else have any other questions or anything?
Yes, sir. So you want us to complete, because on 7.2 we were supposed to do 1 through 6. So go ahead and finish 7.2.
You should be able to finish it now. And it's not due till Yeah, now that assignment 7-2 is due tomorrow at midnight. But now you can finish the whole thing because I did extend it, so there weren't any penalties for it. But you can also, you should be able to do most of 7-3 now also. If you're good, you're free to go.
Thank
I have
you.
a question real quick.
Yep.
Thank you.
Back when we were doing the complementary angles theorem, and we did like A, B, C, and D, like sine 62 equaled cosine 28 degrees.
Yes.
For D, it was cosecant pi over 6, which equaled secant beta, which equaled 2 pi over 6. Would it be okay to reduce that to like pi over 3? Or should we keep it as 2 pi over 6?
Reduce it.
Okay.
Yep, reduce it. Any others? Any other questions? Maddie, did you have something?
No, I just always stay till the end.
Okay. I thought I saw you unmute, so I thought you had a question. Okay, so I'm answering the question for Anne-Marie. This was 7-2, is that correct?
Yes.
Hold on, I need to go as a student here. 7-2, number 16?
15.
No, 15. All right, let me take a look here. Oops, where'd it go? Okay, blah, 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 blah. X, 200, 500 is R, impedance, find impedance, Z, find the values, 6 trig functions. Okay, so let me see here. Oh. Okay, so we have this triangle. R is 500, right? This is 200, and then this is Z. So you found Z by doing 500 squared plus 200 squared equals Z squared. What did you get for Z? I can double check it. Yeah, so it's not, did you get a decimal? No, they want integers and fractions. So you should have got the square root of 290,000. So 290,000. Did you get that? Okay. All right. So now they probably want us to try and clean this up. Did you try doing that?
Yes, but I'm wondering if there's like an easier way to start because I wasn't sure like what to do exactly.
What do you mean start? To clean it up or the whole problem?
Yeah, to clean it up.
Okay, so one way you can do this is you could try and see about breaking this down into things that you know. So like, because it has so many zeros in it, do you agree that 100 might go into this? And 100 is 10 times 10?
Yes.
Okay, so you might start by saying, okay, how many times it's 100 times 2900 underneath this square root? Something like that? Does that make sense?
Yes, sir.
And then you could pull the 100 out as a 10. And then you can try it again. Does 100 go in there again?
Yes.
It does. It goes in there. So you would go 100 times 29. So you already have a 10 out here. So now that 100 comes out as another 10. So that becomes 100 root 29. And then 29 is prime, so it doesn't break down anymore. Is that helpful or not?
Yes, that makes sense now.
Okay, so then now that's what Z is. So did you have trouble with the 6 trig functions or?
No, I just was wondering if there's like a simpler way to reduce it, and you answered that question.
Yeah, there's not really an easier way. I mean, the ultimate easy way would have been for you to say, oh, well, that's just 10,000 times 29. But not everyone's going to see that that's 10,000 times 29. So you go with you start with a number that you're more comfortable with.
Okay. Thank you.
You're welcome. Any others?
Yes, I'm not 100% sure if you'll be able to help me with this or not, but on my calculator, I cannot figure out how to switch between degrees and radians.
Let me see your calculator.
I have the TI 84.
You have to go to mode.
Yeah, there should be a mode. That's the 84 plus. Okay, hold on. I actually have something I may be able to help you.
Okay, I see mode.
You see it?
I was having the same issue with mine. I figured out how to get to radians, but for some reason, whenever I would try to switch, it wouldn't do it.
Like it wouldn't go to degrees for you?
No, it wouldn't go to radians for me.
Okay.
I don't think your screen looks like this, does it?
No.
You got a color screen, right? Or something like that?
Yeah, I mean, yeah, it has color. That's just
Does it look like this?
Or plus
No.
C?
Does it have a mode button?
Yes, it does. I saw the mode
Yeah.
button.
Yeah, and then do you have this sort of thing?
Let me see. Yes, okay, so I see radian and degree side by side.
Yeah, so you just move down arrow and then you move right arrow. And,
okay.
and then once you are like blinking over degree, hit enter.
Okay, so let me try sine 12. Okay, I got the 0.2079.
Okay.
And then you said for the sine 1.7, we had to switch back to radian?
Back to radian because there was no degree symbol on it.
Okay, let me try and see if that works now. Sine 1.7. That was, okay, so sine 1.7 was 0.9917?
Yes, I believe so. Where is it? 0.9917, yes.
Okay. Okay, thank you.
Okay, good,
Okay, got that figured out.
good. All right, we good?
Yes, thank you for teaching.
All right, everyone, have a good day.
Have a good rest of the day.
Yep, you
Thank
too.
you, sir.
All right,
Bye. Thank you.
bye-bye.